Okay, so now we will talk about the motivation of the linear algebra system, why we need to learn such system, what is the benefit of learning system of linear algebra equations. And we will talk about general motivation. So the major motivation of linear algebra equations is just a shorthand representation of the linear system. The major motivation for, you can say, matrices, vectors, notation is as shorthand representation for linear system. Of algebra equations. Okay, and we can make an example. For example, we have a11x1 plus a12x2 plus dot 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 a1n xn equals b1. We have a21x1 plus a22x2 plus dot 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 a2n xn equals to b2. Well, we have nth line, n row of that, which is a n1 x1 plus a n2 x2 plus dot 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 plus a n n x n equals to bn. Okay. Then instead of writing this as linear equations here, we can write as a matrices form, can be rewritten as matrix. And how to write that matrix? So you put coefficients into one big matrices. You put your independent vector x in a matrices. Will be equals to whatever on the right side. Okay, so it's called the coefficient a11, a12, dot 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 a1n. The second row will be 2, 1, 2, 2, dot 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 2n, and you will have n1, n2 until nn. Okay, so that is all the coefficients you write here. You have the independent variable, which is from x1, x2, dot 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 to xn, and you will equals to the right side, which is b1, b2, dot 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 bn. And you can use the matrices, the vectors, such as the a underscore underline to underline, which is represent this 2D matrices, and using the 1D vector to represent as well. So using matrix to represent notation, to represent the multiplication. Here, this A is 2 underline here to represent this coefficient 2D matrices. The X is a column matrices, A times X, will be equals to your final V, which is a 1D matrices. And you can check your dimension whether that is right or wrong. So that is n by n 2D matrices. You have n by 1, so one column, n row, and that will be equals to n times 1, which is also n row but one column in the end. So that is correct dimension. And we will make a multiplication for the linear ODE. We can also use a similar way to represent, which is much simple than you just write as n equations here. Okay, so let's make an example. For example, for chemical reactions. Okay, for chemical reactions, let's make a reaction, which can be complex, can be simple. Let's make 4 reactions. Let's say our reactant is A, and it will pass intermediate B and C goes to final product D. Okay, and it will go through 4 simple reactions. It's like a chain reaction here. It will go from A to B, B to C, C to D. So these are 3 reactions from reactant A going to final product D. For each reaction, it has its own reaction rate, K1, K2, K3. And you can think this as an irreversible reaction, but usually in the chemical reactions, they can be reversible. So they can be, going back. But let's just make a simple case. Then how you write the kinetics of the concentration of the A as function of time, or how you write the concentration of each species as function of time. Okay, so we can have that dCA. The C represent the concentration of the reactant A over dt. So as function of T, differentiate. That is the concentration A change as function of time will be equals to minus K1 CA. Okay, or you can also write CA prime equals this, right? You can also write CB prime will be equals to K1 CA minus K2 CB. So the intermediate B will get from the A part convert to B, but B will consume to generate C. So there will be minus K2 CB part. There is also CC prime will be equals to K2 CB minus K3 CD, right? And then you have the final, which is the product of concentration of the D change as function of time will be equals to K3 C, this will be CC. So this will be CC. Then you basically write these 4 equations here, and you have some initial conditions. So you can solve these differential equations to get what is at the steady state, what is your final CA, CB, CC, CD. Okay, or at any time, what is your concentration look like? You can solve this ODE to get those solution form. But here we are mainly to talk about the motivation of writing this as linear algebra matrices. So what you can get is you can write this D over dt, CA, CB, CC, CD, or you can write this as CA prime, CB prime, CC prime, CD prime. That will be equals to all the coefficients in one matrices and all the independent, variables. So what you can get is basically the coefficient part, which is the K1, K2, K3. So the first will be minus K1, and then CA, CB, CC, CD. And all the other term will be, for first equation will be 0. So 3, 0 here. Then the second part will be K1 CA minus K2 CB. So it's K1 and minus K2 here. Then the other part will be 0, 0. The third line will be K2 CB minus K3 CC. So it's 0, K2 minus K3, 0. Then the last part will be K3 CC, right? So it's K3, 0. So you basically can solve this matrices to get what is your concentration as function, change as function of time. And you can write as this Ca prime will be, sorry, the Ci, concentration of species I, will be equals to this coefficient, this K, and this two underline, which is represented by the rate constant here, the K, times Ci. So you can just use a simple form to represent your complex chemical reaction networks. And that is much simple representation as compared to you write them each individual line, right?